Hey kids, welcome to section 8.6, additional topics regarding hypothesis testing. Today we're going to see how hypothesis tests and confidence intervals work together to give you the same information. We're also going to talk a little bit about the relationship between type 1 and 2 errors and something called the power of a test. There is a relationship between confidence intervals and hypothesis testing. When the null hypothesis is rejected in a hypothesis testing situation, the confidence interval for the mean, using the same level of significance, will not contain the hypothesis mean. So, if we are rejecting the null, then the confidence interval will not contain the mean. Likewise, when the null hypothesis is not rejected, then the confidence interval computed using the same level of significance will contain the mean. So they go hand in hand, they work together, and they are essentially two different views of kind of saying the same thing. So when the null hypothesis is rejected at a significance level of alpha, the confidence interval computed at the 1 minus alpha level will not contain the value of the mean. Also, the null hypothesis is not rejected, the confidence interval will contain. So those kind of these two statements here and these two statements here are pretty much saying the same thing. These results are true for other hypothesis testing situations and are not limited to mean tests. So if you're doing anything with proportions, or if you're doing anything with variance or standard deviation, these same ideas hold true. The relationship between confidence intervals and hypothesis testing presented here is valid for two-tailed tests. That's because if you think about it, a confidence interval has a start and a stop, and that is similar to what a two-tailed test would look like in a hypothesis test. So let's see how these work together. Sugar is packed in 5-pound bags. An inspector suspects the bags may not contain 5 pounds. A random sample of 50 bags produces a mean of 4.6 pounds and a standard deviation of 0.7 pounds. Is there enough evidence to conclude that the bags do not contain 5 pounds as stated at alpha equals 0.05? Also, find the 95% confidence interval of the true mean. Assume the variable is normally distributed. Okay, so we need to see what we have. Well, we have a random sample of 50 bags, so that means n is 50. See, we don't know if this is a z, a t, or a chi-square. So we need to figure out which one it is. Remember, z's go with sigma and with p's. T's go with s's, and chi-square go with sigma squared and sigma. All right, so we got n is 50. The sample mean is going to be 4.6. And it looks like the sample standard deviation, that's S, is going to be 0.7. Since we have an S right here, we know that we are going to have a T test. Since we have a T test, we need a degree of freedom of 49. We also should probably have a mu, since that's what we're hypothesis testing about, and our population mean is 5. So now we go over and do our hypotheses. Our null hypothesis is that the mean is equal to 5. However, we are going to do an alternative hypothesis of not equal to 5, and that's our claim. So when we draw a picture, we're going to shade both sides because it's not equal to. We're going to take that alpha and divide it by 2, so we get 0.025 in each section. Since this has a sample standard deviation, we are doing a t-test. T critical values have a plus or minus when there are 2 of them. If we use our table, we get 2 0.009. So now we need a test statistic for t. That's x bar minus mu over s over root n. So this is going to give me 4.6 minus 5 divided by 0.7 over the square root of 50. Our t critical value had 3 decimals, so our test statistic has 3 decimals. So when I plug this into my calculator, I get negative 4.041. Well, it looks like our cutoff for the critical region is negative 2.009. So our critical value, or our test statistic, I should say, puts us in the critical region, so we are going to reject. So since negative 4.041 is in the critical region, we are going to reject the null. We reject the null. Okay, so our final hypothesis sentence, since we are rejecting the null and our claim is the alternative, there is enough evidence to support the claim. There is enough evidence to support the claim that, and our claim was that the bags do not contain, that the bags do not contain 5 pounds. Claim that the mean is not 5 pounds. Okay, so that is the hypothesis test half. I'm going to put a little mark here. Now we have to do the confidence interval part. Now this is a chapter 7 thing, so you might have forgotten, but the confidence interval is x bar plus or minus t alpha over 2 times the standard deviation s over the square root of the sample size n. So we're going to take 4.6 plus or minus 2.009 times 0.7 over the square root of 50. Now, in case you forget, you round your confidence interval to the same number of decimals as the mean, which in this case is 1 decimal. So I'm going to have my confidence interval is 4.4 is less than mu is less than 4.8. Now, to examine this confidence interval, you're looking for a mu of 5. Well, mu equals 5 is not in the confidence interval. So since it's not in the confidence interval, not confidence level, I apologize, confidence interval. So since 5 is not in the confidence interval, then that agrees with the fact that we cannot support, or we are supporting the fact that it is not 5 and 5 is not in the interval. So these two things are in agreement. If you are rejecting the null, then the hypothesized mean is not supposed to be in the confidence interval. So they agree with each other. They are essentially saying the same thing. All right, let's take a look at another one. This one's about hog weights. A researcher claims that adult hogs fed a special diet will have an average weight of 200 pounds. A random sample of 10 hogs has an average weight of 198.2 pounds and a standard deviation of 3.3 pounds. At alpha equals 0.05, can the claim be rejected? Also, find the 95% confidence interval of the true mean. Assume the variable is normally distributed. All right, so it looks like we are claiming a weight of 200, that's mu. Sample size n is 10. Average weight is x bar equals 198.2. Standard deviation, that's S, of 3.3. That S means that I am using a t-test, which means I need a degree of freedom of 9. All right, so now we write our hypotheses. Our null hypothesis is that mu equals 200, and that is also our claim. Our alternative hypothesis is that it does not equal 200. We are shading both sides because it is a two-tailed test. Take the alpha and divide it in half, so 0.025 goes in each critical region. We have a critical value of plus or minus. So then we look on our t-table, and we get critical values of 2.262. Okay, so then we find our test statistic, t equals x bar minus mu over s over root n. So we have 198.2 minus 200 over 3.3 over root 10. The critical value t has 3 decimals, so my test statistic t has 3 decimals, negative 1.725. So it looks like my cutoff for the critical region is negative 2.262, which means negative 1.75 is not in the critical region, so we do not reject the null hypothesis. Since negative 1.725 is not in the critical region, we do not reject the null. All right, so we are not rejecting the null hypothesis, which is our claim. So our sentence is that there is not enough evidence to reject the claim. There is not enough evidence to reject the claim that the average weight is 200, that the mean weight is 200 pounds. All right, so we can't reject because we don't have enough evidence. Let's look at our confidence interval. X bar plus or minus T alpha over 2 times S over root N. We have 198.2 plus or minus 2.262 times 3.3 over the square root of 10. For confidence interval, we round to the same decimals as the mean. The mean has 1 decimal. So when I calculate, I get 195.8 is less than mu is less than 200.6. So now we want to check and see if our hypothesized mean is in the interval, and it is. So mu equals 200 is in the interval. So if it's in the interval, then we can't reject that it's 200. So I have not enough evidence to reject it's 200. 200's in the interval, so it could be 200. So these are in agreement. Again, you're trying to see if the confidence interval and the hypothesis test are going to say the same thing. All right, so now we got just 2 slides of words. Recall that in hypothesis testing, there are 2 possibilities. Either the null hypothesis H sub 0 is true or it's false. Furthermore, based on the statistical test, the null hypothesis is either rejected or not rejected. And so we have four possibilities that we've talked a little bit about before. So our four possibilities are in this table right here. The null is true and we reject the null. So that's called a type 1 error. The null is false and we reject the null. That's a correct decision. The null is true, but we don't reject the null. That's a good decision. And the null is false and we do not reject the null. That's where we get a type 2 error. So we have our alpha and we have our beta. So a type 1 error can occur only when the null hypothesis is rejected. By choosing a level of significance, say, of 0.05 or 0.01, the researcher can determine the probability of committing a type 1 error. So type 1 errors go with alpha. On the other hand, if the null hypothesis is not rejected, then either it is a true statement or a type 2 error has been committed. This type 2 error occurs when the null is indeed false, but is not rejected. So the probability of committing a type 2 error is denoted as beta. And the value of beta is not easy to compute. You'd think it would be, but it's not. What the researcher usually does is try to minimize the size of beta or maximizes the size of 1 minus beta, which is called the power of a test. The power of a statistical test measures the sensitivity of the test to detect a real difference in parameters if one actually exists. Now, the power of a test is a probability, and like all probabilities, ranges between 0 and 1. The higher the power, the more sensitive the test is to detecting a real difference between the parameters if there is a difference. In other words, the closer the power of a test is to 1, the better the test is for rejecting the null hypothesis if the null hypothesis is in fact false. And so the power of a test is equal to 1 minus beta. That is 1 minus the probability of a type 2 error. Now, as stated previously, the power of a test depends on the probability of committing a type 2 error. And since beta is not easily computed, the power of a test can't be easily computed. You can increase the power of a test by increasing the value of alpha or increasing the sample size. But basically, what you need to know is that it's really hard to calculate beta because it's challenging when the null is false and we do not reject the null. All right, kids, that is the end of section 8.6. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.